All right, let's talk about 6.2, graphs of the other trigonometric functions. So in the last section, we talked about how to graph the sine and cosine function, and hopefully you have those down by now. So now we're going to talk about the other four trigonometric functions, tangent, cotangent, cosecant, and secant. So the good news is if you know how to graph sine and cosine, which you hopefully do, these are no problem at all. The bad news is they look really weird. Not that that should be too big of an issue for you. So let's move on and let's start talking about tangent. So this thing asks us, given the function f of theta equals tangent theta, it wants us to graph two periods, which means we should see the same behavior twice in the same graph. We're actually going to graph more than two periods, but two periods is all that I'm usually going to require from you. So here's all that we need to remember about tangent, is its general shape and its behavior relative to what it is in terms of sine and cosine. And what do I mean by that? I just mean this. We can write, and we should know by now, that tangent of theta is just sine over cosine. So it's sine theta over cosine theta. And if we hearken back to the first part of a pre-calculus class where we learned about domains, we learned that a rational function, that is a function that's defined as, well, it has a division in it, like this is, tangent is a rational function for our purposes. We learned that this thing only gets messed up, as in it's only undefined, when its denominator is 0. So what we need to think about, the question with tangent is, where is cosine of theta equal to 0? Because everywhere that cosine of theta is equal to 0, you're dividing by 0, and that's where tangent is undefined. And you can also just look on your sheet and figure out where tangent's undefined, because we've already filled that thing out. But all we have to remember is, just in our minds, just remember the general shape of tangent. Tangent looks kind of like this. It starts up, it goes down through pi over 2, it touches again here at 1, it comes back up at 3 pi over 2, and it comes over, right like that. So keep in your mind that at pi over 2, cosine is 0, and at 3 pi over 2, cosine is 0. All right. Similarly, you can trace, and it'll do the exact same thing. At negative pi over 2 and at 3 pi over 2, negative 3 pi over 2, cosine will also be 0, which means that at each of these points, here, 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 and here, our cosine will be 0, which means that our tangent will be undefined. And we know that when a rational function is undefined, an asymptote happens. So we just come in here and we put our vertical asymptotes the best we can, straight up and down here. And let's just try and trace that the best that we can. And we're just sketching a graph here. If we wanted to do it exactly, we'd use technology like Desmos or a calculator of some sort. So that'll be good enough for me there and here and sure. So that is your asymptotes, and that's the first thing that you want to draw on every single one of these graphs that aren't sine or cosine. So figure out whether you're dealing with sine or cosine being your problem child, and by problem child I mean the thing in the denominator. In this case, cosine defines your asymptotes. So put asymptotes where cosine is 0, and then just remember the shape, and you're done. So here's the shape of tangent. Tangent looks kind of like x cubed. So you find the origin point right in between two of the asymptotes, and then you have it approach like this from one side, and you have it approach like this from the other side. Okay? We'll continue. We'll put another one in here. So we have it approach like this from this side, and I'll make it a little bit smaller this time so that you can see it. And we have it approach like this from the other side. Now it's going towards the asymptote, but we'll never touch it. Okay? So it'll look something like that. That is tangent, and it will just repeat over and over and over and over again. So tangent is just going to do that over and over and over, and that is a graph of the tangent function. We're going to do this 3 more times for the other 3 functions, but before we do that, I want to give you some information about the general form of tangent, just so that you can have it in your notes. Okay, let's talk about the features of a tangent function. So the standard form is y equals a times the tangent of bx minus c plus d. Keep in mind that what we just dealt with, using theta instead of x, was that the tangent of, I'll use x for this example, the tangent of x, that's all that we said, which means that our b must have been 1 and our c must have been 0 in order to have the tangent of x originally, and our a was 1 and our d was 0 as well. That's the standard values that we worked with. So just keep in mind that when we work with just the tangent of x, that our b must have been 1 and our c must have been 0. That'll be handy in just a second when I define the domain. The stretching factor is the absolute value of a. We call it a stretching factor for the tangent and the cotangent, specifically because it has this shape like this, and it goes off forever upwards and downwards, which means that there is no maximum value that it attains or minimum value that it attains, which is what the amplitude is by definition. In fact, if you look down here, there is no amplitude. The period is pi over the absolute value of b. Remember, in our case, for just the tangent of x, the period would be pi over the absolute value of 1, which is just pi, which means that it repeats itself over and over every interval of pi. Go back and look at your graph and convince yourself of that. The domain is all real numbers such that the cosine of the bx minus c input isn't 0. So that is, the domain is this guy right here, all x, that does not equal c over b plus pi over 2 absolute value of b, k, where k is an odd integer. If I were to give you a version where a, b, and c and d were all different numbers and I just translated and moved it around and whatnot, this would always give you the domain. But for just tangent, and this is worth remembering, the domain of just the tangent function, so just d tan here, is, and then I'll give it to you here, it's all real numbers except for, this means set minus, except for the set containing, and look, it's just, if you come in here and you plug this in, these values right here that I said would be useful in a second, if c is 0, this term dies in a fire, and if b is 1, this just becomes pi over 2k. This whole thing just becomes pi over 2k, where k is an odd integer, and you know the odd integers. It's positive and negative, 1, 3, 5, 7, 9, so on and so forth. So we're going to say all the real numbers except for the ones that are a problem, which are the places where cosine is 0, which means that you're dividing by 0. Look back at the previous graph that we just drew. I just need to list the negative and positive odd integers and multiply them each by pi over 2. That's easy enough. So we'll start with, let's just start with negative 3. So negative 3 pi over 2, and then the next one will be just negative 1 pi over 2, then the next one will be just pi over 2, then the next ones will just be 3 pi over 2, and then we continue onward and forever. Okay, and you're welcome to put more of them if you want to, but really this is just all real numbers except for where, this is just where cosine equals 0. So it's just all of the real numbers except for just where, this is just where cosine equals 0. That's everything inside of here is just where cosine equals 0. So just put in a list of some of the places where cosine equals 0. And it's just the negative and positive odd versions of pi over 2. Remember it however you want to, but honestly, if you can remember the cosine, which you should be able to remember, where it equals 0 at is what you exclude, that's what this means, from the real numbers. That's your domain. That's everything that you're allowed to plug into the tangent function. And if you look at your sheet, you'll notice that, these aren't on your sheet, but if you look here and here on your sheet, that your tangent should be marked as undefined there because it is. The range, thankfully, is just all real numbers. That's easy enough to remember. And of course, it's all real numbers. I just said that the shape was like this. It goes up and down forever. There's no breaks in it. That's great. The vertical asymptotes just occur everywhere where there's an asymptote. Well, everywhere there's an asymptote is everywhere that we broke, which is just up here. So these two things should look exactly the same, which they do. There is no amplitude. We talked about y. And then the function y equals tan theta is an odd function because it's the quotient of an odd and even functions. That is, it being an odd function means that the tangent of negative theta equals negative tangent of positive theta. It means that you can pull the negative sign out. That's what odd function means. So get all that down. It's worthwhile to have. The things that I'm really going to need you to remember is the period for when b equals 1, The domain, which I just showed you here, and the range are the three main things that you're going to need to repeat to me on a test at some point, but the rest of it will come in very handy at varying points in the future. Let's move on and talk about cotangent. So given the function f of theta equals cotangent of theta, we want to graph two periods. Let's move down a bit and let's go ahead and do that. So remember, we're graphing cotangent here, and I'll put it over here for you really quickly. F of theta equals cotangent theta. Cotangent, of course, remember that cotangent is just cosine over sine. And this time, the guy that's messing everything up is sine. So you'll want to think about in your head, you don't have to draw it, but think about in your head the sine function and kind of how it behaves, which of course you know the sine function by heart. So here we go. There we go. And just draw the sine function. Now, when you're drawing these, you're welcome to draw the sine function on your paper. Do it in very light pencil because you have to erase it when you get done. But if you want to use this, now we know that the marks need to be put. Sine is 0. That is, you're dividing by 0 at 0, pi, 2 pi, negative pi, and negative 2 pi. That is integer multiples of just pi. Awesome. Keep that in your head. We'll go ahead and delete all this. So remember, sine was 0 here. Sine was 0 at pi, sine was 0 at 2 pi, sine was 0 at negative pi, sine was 0 at negative 2 pi. So at each one of these you put an asymptote because you divided by 0 there in the function. That should make sense. So this is the one that everyone forgets on the y-axis. Make sure to do it. If you're drawing over top of it, the important part is this thing ends up here. Make sure to put your dashes up above it and below the y-axis as well, just to make sure. Or you can do what I do, which it's not exactly correct, but it's easy to see. Just draw the asymptote like right beside of it. Just right beside. I know that you mean that it's on it. I know that you don't mean to go over. Just draw it right beside of it so that you can actually see it. If you're doing it on a sheet of paper, I won't be able to see it otherwise. So just make sure that I can see that asymptote. If you do draw it directly on top of it and I'm unable to see it and I take points off for it, that's on you, not me. I wasn't able to see it. Just either put it beside of it or just make sure somehow or another that I know that there's an asymptote there. It'll also go through at pi because sine of pi is 0. It'll also go through at 2 pi. And of course, the problem only wanted us to graph 2 periods, but we're going to graph a whole bunch. 2 is the most that I normally ask you to do. I could ask you to do 4, though. It's not like it's that hard. So remember, the period is the amount of time it takes for a function to repeat itself. In this case, it's pi again. Notice the distance between here and here is very clearly pi. So your period must be pi. I have to erase this so I can actually do it. And then just remember the shape of the cotangent graph. Come exactly in the middle, just like you did with tangent. Except instead of going up this way like you did with tangent, okay, instead of going up this way like you did with tangent, just go up the other way. Just reflect it. Like this. And just repeat it over and over and over again. And this is the cotangent function. Just every single little dash in between here, that's the cotangent function. And this has to do with sine goes up originally, so the tangent, which was governed by sine, goes up first. This function is governed by cosine up top, which decreases immediately, which is why this decreases immediately. But come on in here and look at this. Look at this. Come on down. There you go. That is the cotangent function. It's not just 2 periods, it's 4 periods, which is awesome. So there's 4 periods of the cotangent function. You just have to remember the shape and where to put the asymptotes, and everything else falls into line very easily. Let's move on and let's look at some features of the cotangent function. So this should look very familiar. I'll let you pause the video right before we move on, and you can get all this down. The general form looks amazingly like tangent. The stretching factor is exactly the same. The period's exactly the same. The domain is such that your sine theta isn't equal to 0. And I mean, if you want to be technically correct here, it's sine of bx minus c does not equal 0. But just keep in mind that the domain is all the places where the sine of whatever your argument is So call theta bx minus c, and we're good to go on that. The domain is, it looks exactly like the domain for tangent rather, except there's no 2 down here. It's not multiples of pi over 2, it's just multiples of pi. So it's actually even easier. So let me write this out for you. The domain of sine is just all real numbers except for integer multiples of pi. So negative 2 pi, negative pi, 0 pi, which is 0, negative 1 pi, 2 pi, and then don't forget to go on to infinity, and don't forget to come from infinity too. So dot, dot, dot like that. And there you go. That's your range, that's your domain rather for sine. It's all real numbers except for integer multiples of pi. There's other ways to write this if you wanted to, but I've found in the past that it only confuses people. But if you insist, and I'll let you go back and do this for, this is for cotangent, by the way, not sine. This is for cotangent. But if you want to go back and write that the domain for cotangent is the set of all numbers x such that x is not pi k, where k is some number like that. You could go through and do that, but honestly, don't even bother with it. The domain of cotangent, that's cotangent, is all real numbers except for integer multiples of pi. That's pretty easy. Integer multiples of pi is 0, 1, 2, 3 pi, negative 3 pi, negative 2 pi, negative 1 pi, negative 75 pi, whatever. Negative integers multiplied by pi. Throw those out because that's where sine equals 0, so that's where cotangent's divided by sine. Your cosine's divided by sine is cotangent. Probably worth keeping that in mind. Cotangent theta is cosine theta divided by sine theta. So anywhere that we're dividing by sine, which is these places, is where your domain is. And I hope I've beaten a dead horse to death and that's crystal clear to you. The range is all real numbers, of course, because it does this behavior over and over. Goes up to positive infinity and down to negative infinity over and over, so there is no maximum and everything's attained. There is no amplitude for the same reason as tangent. Vertical asymptotes just occur everywhere that the domain's broke, because that's how math works. And then it's an odd function for the same reason as tangent. That is, once more, cotangent of negative theta equals negative cotangent of positive theta. That is what that means. So go ahead and pause it. Get all that down. Remember, the main things I'm asking you to do are the domain, the period, except with b being 1, so the period is just pi, is what you need to remember, and the range is all real numbers. Those are the 3 things that I'm going to ask you to remember, in addition to being able to draw several periods of the function. So now we're asked to graph 2 periods of the secant function. So these last 2, secant and cosecant, get really, really weird. And we can sort of think about what's going on with it pretty easily, but I want to move down and get the entire graph in screen so that we can do that. All right, so let's talk about secant. So let's write it up here again. So this is f of theta equals the secant of theta. And remember that the secant of theta is 1 over the cosine of theta. And you have to remember that. If you can remember this, you're good to go, because here's what we're going to do. Exactly like we did with tangent, we're going to think about the cosine, and we're going to draw the cosine. So let's draw the cosine. Draw the cosine. Draw the cosine. Actually, let me just draw the cosine in red, not a red dotted line. Let me just do cosine in a couple of pieces here, so that I'm going to have to delete it later. So when you draw this yourself, try and get it as good as you can, but try and do it with a light pencil mark. Please never do this with pen, because we're going to erase this in the end. Okay, that's not the best, but we're just trying to sketch it. There we go. So it bounces back and forth between -1 and 1, and that is, what I just drew is not secant. What I just drew is, that is cosine of theta. So what we need to know from this is everywhere there is a 0 of this function, there needs to be a asymptote. So put the asymptotes everywhere that there's a 0. Now those are going to stay on the graph, so I can use dotted lines for that. I don't want to use dashed lines for it in the video because I have to individually cut every single dash if I want to delete them real quick. Now that I've already moved past it, the undo tool won't work for me, in case you're just wondering. I'm mainly just talking right now so that it's not dead air while I'm drawing. But I'm just putting the asymptotes where the cosine function is 0, because that's how math works. So let's finish that up. So there we go. And then here's how this is going to work. And this is bizarre, but we flipped cosine. So here's how this is going to work. I'm going to draw it in blue. I'm going to draw the actual secant function in blue. We're going to come up here to this maximum right here. And we're going to flip this bowl. We're going to flip this bowl upside down. We're going to flip it because we flipped it over here. So I'm just going to flip this bowl upside down. Then I'm going to come down to here, and I'm going to flip this bowl upside down. And so what I'm drawing is the secant function. I'm going to come right here. I'm going to flip this bowl upside down. Right, like that. And I'm going to come right here, and I go off the screen to draw it this way, so I don't need to draw it. I run out of graph there. I don't need to draw that part, but I could draw this part. And then over here, I go off of the graph to draw this part, so I don't need to draw it, but I probably should draw this part. And there we go. That is the secant function, except what we do then is we go get our eraser and we erase the cosine that made it. And that is the secant function. I'll get rid of this cosine. That's the secant function that we just drew. So it's a really weird, messed up looking equation, function of an equation rather, but it's not hard to do. You just remember that you flip it. You remember that secant goes with cosine. That's the most important thing. Otherwise, you would be doing cosecant. You draw cosine, which is why I had you memorize what cosine looked like so much. And then you just flip everything, because that's all that you did over here. You get your asymptotes the same way that we did for tangent and cotangent, and you're done. And this is how you do secant. And that's it. And if we were to want to manipulate this by adding in numbers here or whatever, we just manipulate the underlying cosine, however we're going to do it, and then draw the secant back on top of it, which is something that I know that we're all capable of. So that is the secant function. Of particular note, the period is pi over 2. The period is pi, rather. Lord, the period is 2 pi, because it takes from right here to right here before it starts repeating itself. It has to do the whole downward bowl and then the whole upward bowl before it starts doing a downward bowl again. So the amount of space in between here and here is the period, which is 2 pi, which we'll talk about in just a second. Okay, so please don't say that the period is pi because each one of these chunks is pi. It has to do one of these guys and one of these guys before it starts repeating, and the period is the amount of time it takes a function to do its whole business before it starts repeating again. But if you thought about just taking this whole screen that we've got, everything in here, and just laying it end to end, so starting right here, moving it over to here, and starting again, it would keep making the same pattern on and on forever. So it definitely is a periodic function. So we're going to notice a lot of really weird things about this when we go through the characteristics. Namely, the range is weird. It's everything but -1 to 1. Notice how there's a lot of dead space in between here, which is a fantastic horror video game if you all have never played it. But everything in here is not part of the range because everywhere was there for cosine, and you're not able to ever get any of these points out. You can try, but you'll never get a proper fraction out of a secant function. Just an interesting little thing. And that is used in signals processing in some points. That little property is very useful if you always want positive and negative alternating signals that are never fractional. I have seen that in some applications before. It's a very useful function. Let's talk about its properties, and then one more function and we're done. Features of a secant. The general form looks like the general form. The stretching factor, again, there is no amplitude for this because it goes on forever in both directions. The period is 2 pi over absolute value of b. We talked about why. The domain is all real numbers so that cosine isn't 0. And I'm just going to let you go back in your notes and notice this, but the domain of secant is the exact same thing as the domain of, was it tangent or cotangent that divided by cosine? It was tangent. So these are the exact same thing. So if you want to go back to tangent and write out its domain, that we said, the all real numbers, set minus, blah, 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 that stuff. Go ahead and put that in your notes, please. But I just want you to make this little thing here, this little note here, because if you can get the domains for tangent and secant, if you can get the domains for tangent and cotangent down, then you'll have the domains for the other two things, and you know how they're related because secant has cosine in the bottom and tangent has cosine in the bottom. The same thing for cosecant and cotangent with sine in the bottom. So they have the same domains because they break in the same place and they have asymptotes in the same place. And wow, math sure does have a lot of patterns, doesn't it? So the domain is all these places. The range is every real number x such that x is not in the domain of cosine. That is, just put this in your head. It's everything from negative infinity to negative absolute value of a plus d to absolute value of a plus d infinity. That is, for us, and I'll write this out for you, the range of secant is all numbers from negative infinity, okay, from negative infinity to 1, including 1, negative 1 rather. Notice that right there. Union, and then we come from positive 1 to infinity. That's how we say skip all the numbers between negative 1 and 1. So that's the range of secant. Keep that in your head. There is no amplitude, and it's an even function because cosine's an even function, and that means that the secant of negative theta is the same thing as the secant of positive theta. That's what that means. So keep all of that in mind, but remember the main things I want you to know are the range, the domain, and this would not be acceptable for you to write on a test. I would actually want you to write instead of this, write the actual domain of tangent out here, please, which is just this right here. So it's pi over 2 is the thing that we're doing. So that's the one that goes negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, and then we include it for forever. And it's not a issue of memorizing that, guys. This is just, these are all the places where cosine is equal to 0. That's really all you have to have in your head. I do not memorize this otherwise. That's the domain for secant. So you'll need to know that, the range, and of course the period. And for just secant, the period is just 2 pi. For just secant. If we don't put anything on here, then b is 1, and this whole thing is just 2 pi. For the general form, it's what I said it was. Okay, so remember that the period is 2 pi. Basically, the period is 2 pi for everything except for tangent and cotangent. The only two functions that have both sine and cosine in them. For tangent and cotangent, it's pi. I get people every year with that, though, and I'm sure I'll get someone with it this year. Just be careful. Let's talk about cosecant, the last of these guys. So we want to graph two periods. We're going to do multiple periods, of course, but we want to graph two periods of the cosecant function. Let's get the graph in frame and do that. So we want to do cosecant now. So let's keep in mind what cosecant is. So f of theta equals cosecant theta. And let's remember that the cosecant of theta is just 1 over... Now look, it's the cosecant. You would really want this to be the cosine, wouldn't you? If cosecant and cosine went together in this relationship, but they don't. It goes together with sine. Cosecant is 1 over sine, which means that sine is the thing that you need to draw and later erase to figure out the asymptote. So let's start with that. Let's do sine. Sine looks like this. Sine starts at 0. It goes up to 1 at pi over 2, comes back down to 0 at pi, comes back down to negative 1 at 3 pi over 2, and then comes back up. And then it just continues its business on the other side here, all the way like this, like that, right? So just keep in mind that that's the behavior, right? So I'm just going to draw this a little bit better with a solid line now. So you can follow along with me. Just come on up here, and then down through here, and then right through there, like that. That's half of it. And then we can come right on down here and just do sort of roughly. Remember, you are going to be erasing this. You are going to be erasing this. That's not good. You are going to be erasing this, though, so let's get... Awesome. That's a very rough sine, but it is the sine. And then that's going to get erased. So of course what we need to do is put in the asymptotes now. So basically everywhere that this thing is 0, so there, at pi, at 2 pi, there was the origin. Negative pi, negative 2 pi, those are all going to get asymptotes. And again, please don't draw right on top of this. I can't see that. Either draw beside of it or make sure that it extends both above and below the actual arrows. I'm just going to do it right beside because that's good enough for me. That's just so that I can see it. It's not actually just to the left or just to the right. It's on top of 0. It's just you can't see it when you draw on top of that. Do the same thing for pi. The same thing for 2 pi. Wow. The same thing for 2 pi. We'll do the same thing for pi over here, negative pi over here rather. Back here in these quadrants, and then the same thing for negative 2 pi. And there we go. That is our asymptotes kind of roughly done. Now we're just going to draw cosecant, and I'm sure that you've already figured out how we're going to draw cosecant, but cosecant is just sine flipped, so we just come to the tops of each of these and we just flip them like this. Wow, that's bad. There we go, like that. Okay, and when you're trying to do these for me on a test, make them as neat as you can. Take your time. You all have the benefit of doing this on a piece of paper with a pencil, which you're very familiar with. Doing this on a tablet is a completely different monster altogether. So I know you can do better. And then just keep in mind that when you get done, you need to go back with your eraser and erase the sign that you drew, like that and like that. And what's left is cosecant. That's a graph of cosecant. It looks an awful lot like the graph of secant, but go back and look at the graph of secant, and you'll see the differences. Namely, they look almost exactly the same. It's just one of them is shifted over pi over 2 from the other, and that's true either way you look at it, depending on what you mean by over. So this is cosecant, and it has properties just like secant. I'm going to scroll down and let you get it, and then I'll give you the domain and the range and all that, and we'll be done. But that is cosecant. Make sure that you got that down in your notes, and we'll move on. Last bit of writing. The features of the cosecant function, there's this general form. Its stretching factor is absolute value of a. It's called a stretching factor. There is no amplitude for this, so there's only amplitude for sine and cosine. The rest of them don't have amplitudes. They have stretching factors. The period is 2 pi over the absolute value of b. For us, of course, we're using just cosecant to draw, so our period is just 2 pi over the absolute value of 1, so just 2 pi. The domain is all real numbers such that your sine isn't 0. That is, such that your sine of theta, if you call all that theta, isn't 0. That is, your domain of the cosecant is all real numbers except for integer multiples of pi. So this is the easy one. So comma, put some dots in front of it. Negative 2 pi, negative pi, 0. Don't forget 0. People do that all the time. Pi, so on and so forth like that. I get the point from there. That's the domain of cosecant. Also keep in mind, this may help you out in the future, that the domain of cosecant is the same thing as the domain of cotangent. They have the exact same domains because of course they do. Both of them are dividing by sine. So they're going to have the same domain. They're going to break in the same places. They don't look the same, but they're going to break in the same places. So the domain is this like it has been. The range is all real numbers such that x is not the domain of sine. The range of cosecant is exactly the same thing as the range of secant. And it is just all numbers from negative infinity up to negative 1. We allow negative 1. And then we go on, hop on up to 1, and we go on to infinity. That is everything but negative 1 to 1 is what we do. But we also do allow negative 1 and 1. You can get negative 1 and 1 out of these. So the vertical asymptotes occur at the same places that the domain breaks. Of course, that makes sense. There is no amplitude, like I said, and the function is odd because sine is odd, and cosecant is just 1 over sine. So cosecant of negative theta equals negative cosecant of theta. Odd function means you can pull the negative out. Even function means that the negative just goes away. If you have a negative input, it's the same thing as a positive input. That's it for all of this. So go ahead and get all that down, and we'll move on to inverse functions after we draw these 4 functions several dozen times and get them in our head. But thank you. Stick around. The next thing that we'll do is inverse trig functions, and then we're done with this unit. So I'll see you in the next one.